So we're going to complete the last section in our D5, which is derivative applications. So we've done related rates, we've done optimization, and now we're going to kind of think about the motion problems. So with motion problems, suppose that we have an object and it's moving in a straight line. We're going to refer to the position function of that object as S of t. So this is the position of the object at any given time t. Okay. Sometimes you'll see that different textbooks refer to this in different ways. Some position functions are referred to as x of t. I'm just used to using s of t, so we can do that. Now, some definitions. The average velocity, since they've given me 2 time points here, I'm not doing an instantaneous rate of change. I'm not doing a derivative, but I'm doing an average velocity, which is an so when I'm doing average velocity, I'm doing slope of a secant line. If I'm talking about one time interval and I'm saying what is the velocity at this time, I'm looking at an instantaneous slope. Instantaneous slope or slope of a tangent line. So you'll notice that when I'm doing an average velocity, I'm doing a change in position. So those are like my y coordinates subtracted together, divided by a change in time, which is kind of my x coordinate subtracted, so it's just a slope. You'll notice that the instantaneous velocity, or the velocity at time t, is the rate of change of the position with respect to time, but we're interested in the derivative because we're at one specific time point. You can see I spelled instantaneous wrong. So you have to come back to that idea of the difference between a slope of a secant line versus a slope of a tangent line. The slope of a secant line gives you sort of an average, and the slope of the tangent gives you kind of at that moment. Speed is kind of a magnitude quantity. It has no direction. So if we want to do that, we take the absolute value of our velocity function. And the absolute value of our velocity function is just the derivative of the position function. Average acceleration, we do, again, it's an average, so it's a secant line. We do change in velocity over a change in time. Or my acceleration at a time t, which is one time interval, is one derivative of the velocity function. And if I have the velocity function, I could do 2 derivatives of the position. So I like this little flow chart to kind of summarize it. If I start with position, I take one derivative and I get to velocity, and I take a velocity derivative to get to acceleration. Or if I'm looking at position, I can take 2 derivatives to get to acceleration. In terms of integration, I can start with an acceleration function, go back to a velocity and back to a position, but we will learn that kind of in our I units or integration stuff. I1 through I4, we'll get a handle on how to do that. Now, just sort of a reference table for you. Our questions won't get too particular, but if they talk about the velocity of a particle, or whether the particle is moving right or left, or if the speed is increasing or decreasing, if my velocity is positive and my acceleration is positive, or if my velocity is negative and the acceleration is negative, my speed is both increasing. The only difference is one particle is moving right and one particle is moving left, but they're both increasing in time. If my velocity and acceleration are opposite signs, so one of them being positive, one of them being negative, my speed is decreasing in both scenarios, but one particle is moving right and one particle is moving left. Okay, so we're going to go through and just do a couple of examples here. I give you a position function, and we're going to be interested in time being positive. So how do I find the velocity function? I take a derivative, so minus 4t plus 12. To get my acceleration, I take one more derivative, which is minus 4. It says to graph the velocity and acceleration on the same grid. So I'm going to draw sort of a vertical line coming down here and a horizontal line here. So there's my time, and this is going to be my y, and I'm going to label which one is acceleration, which one's velocity. So I'm going to do my acceleration in blue. My acceleration is always -4. So this is a of t equals -4. If I want to do my other function, which I'll do in purple, my x-intercept would be +3, because that will make y 0. And my y-intercept is +12, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, approximately there. And this is a decreasing function. The slope is negative, and this is my velocity function. So you may have to graph these functions, just simple quadratics, linears, cubics, and so forth. Now it says find the velocity at these very specific times. Now, since there's only one time interval given, I'm just going to take my velocity function, which is -4t plus 12, and I'm going to sub in my different time intervals. V of 0 is -4 times 0 plus 12, which is 12 meters per second. I'm going to assume we're working in meters per second. My velocity at 1 is -4 times 1 plus 12, so that's 8 meters per second. My velocity at 3 is -4 times 3 plus 12, which is 0 meters per second. My velocity at 5 is -4 times 5 plus 12, which is -8 meters per second. It says find the average velocity and the average acceleration for the time interval. So I'm given an interval of time, so I'm looking like for a slope of a secant line. So velocity average is equal to the change in position. So position at time 2 minus position at time 1 divided by my 2 time intervals. So S of 4, now my S of t function was given above. It's -2t squared plus 12t. So my position at 4 is -2 times 4 squared plus 12 times 4. Minus my position at 1, -2 times 1 squared plus 12 times 1, all divided by 3, and then you carefully work out that value, which I'm just going to use my calculator for. So I'm going to store 4 in my calculator, type in my position function 2x squared minus 2x squared plus 12x, and I get 16 minus, I'm going to sub in 1 into my function, and I get 10 over 3. 16 minus 10 is 6. 6 divided by 3 is 2. So the average velocity over that time interval is 2 meters per second. But at any given moment, my car may not be traveling 2 meters per second, or the object may not be traveling 2 meters per second. My average acceleration is the change in velocity over the change in time. So like the slope of the velocity graph. So my V of 4 is -4 times 4 plus 12, which is -4, minus my velocity at 1, which we worked out above to be 8, divided by 3, minus 16 plus 12 minus 8 gives me -12 over 3. So my acceleration is -4 meters per second squared. So my velocity and my acceleration have opposite signs. It means my object is slowing down, and you can use the chart to answer more questions related to that. So now what we're going to do is we're going to find the time so that the position is -32. My position function is given by -2t squared plus 12t. Now you'll notice in the majority of these examples I've given you nice polynomials, But in these examples, the polynomials don't have to be nice. They don't have to be polynomials. They can be weird trig functions, log functions, e functions, anything I want. You just kind of follow the same ideas through the whole thing. I want to make my position equal to -32, and I want to figure out what time block gives me that. So I'm going to move everything over so my leading coefficient is positive, which means I'm moving everything to the left. I'm going to divide everything by 2. T squared minus 6t minus 16 equals 0. 8 times 2 is 16, so t minus 8, t plus 2 is my factored form for that quadratic. So t is equal to 8 and -2, but we're not considering negative time. So when t is 8 seconds, and we're assuming I'm working in seconds, my position will be -32. When is my velocity -16? Well, I need to take my velocity function, which is one derivative of position. Whoops. So the derivative of my position graph is -4t plus 12. I'm going to set that equal to -16. Solve for t. So -16 minus 12. -28 is equal to -4t. So t is equal to 7. So when t is equal to 7 seconds, we'll be able to know when the velocity is -16. Find the time when the object reaches its maximum height. So now we're looking for a maximum height, which is like a local max here. And when I'm trying to find a local max, I take the original function, I take the derivative. So my velocity function is -4t plus 12, which is the derivative of position. I set the derivative equal to 0 to find my critical points. So t is 3. I draw my number line. We're not going to go below 0. I'm going to test my derivative and then say something about my position. So when I sub in a value for time that's between 0 and 1 into this derivative, simplified derivative, I'm going to get a positive answer. And then when I sum in a number like 5, -20 plus 12 is negative. So there's going up, decrease, or increasing to decreasing. So I'm going to say local max at 3, and where is the maximum height? I sub it back into my position function to find the y coordinate. So that would be 3 and -2 times 3 squared plus 12 times 3 is 18. So find the time when the object reaches its maximum height. My time is 3 seconds. My maximum height is the y coordinate, which I've already done. And my y coordinate is 18 meters, because I'm assuming my units are meters per second. So this unit is quite short, this little lesson. I kind of gave you the key ideas kind of through the first slide. Whoops. The first slide and the second slide here. So what you're going to do is continue doing these problems, number 2, number 3, and that's sort of the key ideas of this section. So just make sure that you understand this little flow chart right here, because that kind of gives the bulk of what we need to know. I give you a original, you take a derivative, get a velocity. I give you the velocity, you take one more derivative and get the acceleration. And sometimes they may ask you questions relating to this chart, so your chart is also important to know. So that's the lesson for today. Please complete the rest of those problems, and the solutions are posted for you on D2L.